we're going to look at a very straightforward torque analysis problem. And what I have here is a beam, and it's sitting on a fulcrum, so a pivot point at this point. And I have one mass of 0.4 kilograms that's positioned 0.4 meters away from the center. And then I have two masses, one at 0.2 meters away and the other 0.2 meters away from that. And so the question is this object in balance? Is the net torque on this object zero or not? What is the net torque on this object? And given what the net torque is it going to rotate, and which side will dip down, if at all? So this is going to allow us to practice that very straightforward process of an extended free body diagram, looking at all the forces acting on the object we're interested in, and then of course the torque analysis and how we look at net torque, and then determining the total analysis. So, oops, I dropped a macro. All right, so the first thing we have to identify in this analysis is our object of interest. So what is the object that we're interested in? Well, we want to look at the rotation of that beam. So the beam becomes our object of interest. All right, so then we have to look at the forces acting on that object. So what are the interactions? What are the objects interacting? Well, we know, let's call this mass A, B, and C. So we know that there is a force by mass A, and that's between the beam and mass A. All right. We also know that there's a force of mass B between the beam and mass B. And we have mass C. So we have the force of mass C between the beam and mass C. Now what else is interacting with this object? Well, we know that the force of gravity always interacts. So we have the force of gravity that's between the beam and the earth. And, well, that beam is resting on this fulcrum, that pivot point, that anchor point. And so there's an interaction there. They're touching each other. We've called that type of interaction a normal force before. So we'll call it a normal force in this case. It only exists because that beam is resting on that pivot point, and that's between the beam and the holder. All right, any other interactions? Nope, I don't see any other interactions either. So these are our 5 interactions. Now we're going to take that, and instead of that free body diagram like we did in our force analysis, we're going to draw an extended free body diagram of the beam. All right, so I like I mentioned in the video on the free body diagrams, I like to draw my free body diagram in the orientation that the object is. And then we start putting the forces where they are acting. So force A is at this end of the beam. So here's force by object A. Force B, well, that's at this location on the beam. Force B, and why do you think I drew that arrow about half the size? Well, it's half the mass, and the force that's acting on this object is indeed the gravity due to that mass. So half the mass, half the force of gravity. All right, we have force C that acts on the end of the beam. Again, it's going to be as the result of the force of gravity acting down on that mass, and so force C and force B probably look alike. They're the same mass. And then we have the force of gravity on the normal force. So we talked about in the center of mass lecture, and then in that extended free body diagram, that the force of gravity we know acts at the geometric center of a uniformly distributed beam. I didn't mention that. We're going to assume a uniformly distributed beam in this case. I don't really know how long it is, so I'm just going to guess at the length. I'm not given the mass of the beam. We'll find out if that's important for us or not when we do the analysis. And then the normal force. Well, that's acting up. Now I can give a guess at how big the normal force is. If this object isn't moving up or down translationally, and then we learned in our force analysis and our conceptual ideas, free body diagrams with forces, that the ups have to match the downs. It's balanced if it's not moving up or down. And it's not. It might rotate, and we're not going to talk about that motion up or down. So all the downs have to be countered by that upward force. So I know the normal force is going to be pretty long relative to those pointing down. All right, so here's our extended free body diagram, and we're ready to take that information, look at the torques, and look at the net torque to see what this object will be doing. So I have 5 forces, so I'm going to have 5 torques that I'm going to analyze. And when we look at torque, we want to remind ourselves that the torque is the force perpendicular times the radius that that force is acting. That force perpendicular, again, is between the object and the radius. So what is the perpendicular component if we compare the force of the object to the radius? So we needed to figure out the radius, which means we need a pivot point. Now, I don't know the force of gravity acting on this block, and I sure don't know the normal force. So I'm going to be clever about where I put my pivot point in the analysis. I'm going to put my pivot point at the location of the force of gravity and the normal force. Why might I do that? Well, if I go to calculate the torque due to the force of gravity or the torque due to the normal force, my radius is going to be 0. And if my radius is 0, my torque is 0. So it doesn't matter how much that beam weighs, and it doesn't matter what the interaction is between the beam and the stand. Neither one are exerting a torque because there's no radius. So I'm going to be clever about where I put my pivot point in analyses. I might want to select it where I don't have information about the magnitude of the force, so I don't have to worry about the torque exerted by that particular force. All right, so now let's look at all 5 of these. I like to number them, kind of help orient myself as I go through the torque process. So we're going to calculate the torque on each one of these objects. Then we're going to look at the net torque and see if that tells us something about what the behavior of this beam will look like in this situation. So, torque 1. Well, torque 1 is due to the force by object mass A. So that's going to be the force from mass A times the radius for mass A. Well, the force exerted by mass A is its weight, the force of gravity of mass A. So I have the force of gravity of mass A times the radius of mass A. It's already acting perpendicular, so I don't have to worry about that angle. And this particular example is ideal for our conceptual-based physics course, and therefore everything we're going to do in that course will be at 90 degrees. If you're looking at this video for the more algebra-based or calculus-based type physics, you would take the sine of the angle to get the true cross product, and the sine of 90 degrees, of course, is 1. So we won't continue with that sine analysis now, since all of these are exerting a 90-degree angle. All right, so the force of gravity of block A is the mass of A, which is 0.4 kilograms, times 9.8, times the radius. Now remember, that radius is from the pivot point to the force. From the pivot point to force. That is 0.4 meters. And then what I want us to think about is whether or not this is a positive or a counterclockwise torque, or a negative or a clockwise torque. So this force would cause the object to rotate in the counterclockwise direction. This direction, therefore, we have a positive torque. Remember, if you're going to be doing an angle analysis, this would be the right-hand rule, where we're pointing our fingers in the direction of the radius, extending that radius, curling to the force. That's a positive angle, positive 90, positive 1. All right, so a positive torque. Okay, torque number 2 is due to the force of gravity. Well, we already kind of talked about that one, right? We said that it's going to be the force of gravity, whatever that is, times the radius. Well, the pivot point's at that force, so this is automatically 0. There is no radius. Okay. Force number 3 is due to, torque number 3 is due to force of mass B times the radius of mass B. And like force number from A, torque number 1, the force is going to be due to the force of gravity of object B and its radius. Well, that's the radius from the pivot point to the force. So this is radius B. And we know that to be 0.2 meters. So we have 0.2 times 9.8 times 0.2 meters. And then again, we want to think about, is it counterclockwise or clockwise? Will this force cause a rotation in the clockwise direction or the counterclockwise direction? Well, if I'm anchored at my pivot point, force B is trying to go in the clockwise direction. So that's that way. That's a negative torque. All right, force 4 is causing torque number 4. So that is the force of object C times the radius of object C. Now I always want to be careful here. That radius is from the pivot point. So that's this radius there, radius 4, and that's 0.4 meters. So we have 0.2 kilograms times 9.8, the force of gravity of object C, times 0.4 meters. And then we want to look at whether or not it's a positive or a negative torque. Again, this force is going to try to rotate that object in the clockwise direction, and so it's a negative torque. All right, and our last force, torque 5, is due to the normal force times the radius of the normal force, and well, again, that's at the pivot point, so that radius is 0. So that is not going to contribute a torque. Okay, so if we want to know what this object is going to do, it's really the net torque. All the torques acting on it causes the object to rotate, or change its rotation. So we have to add all of these torques up. All right, so we're going to do just an algebraic sum considering our directions. So I'm going to put these values into numbers. We have 0.4 times 9.8 times 0.4. So the torque exerted by object 1 is 1.568, and we said that was positive, so we'll keep that positive, plus 0, plus 0.2 times 9.8 times 0.2, that's 0.392, and we said that is negative. So we're going to make sure we consider that negative value. Let's put that in parentheses. Plus 0.2 times 9.8 times 0.4, and that is negative, again, 0.784, again, because it's a clockwise rotation. And so we want to make sure that we have that negative value. So now I can add all these up. 1.568 minus 0.392 minus 0.784. And I see that my net torque is a positive 0.392 Newton meters. Remember, is our unit for torque. Okay, so first of all, it's non-zero. And if it's non-zero, that tells us that they are not balanced. And indeed, the object is going to rotate, change its rotation. A positive value tells us that the rotation will be in the counterclockwise direction. And so the net torque acting on this bar is positive 0.392 Newton meters, meaning it's going to rotate in the counterclockwise direction, and this side is going to tip up. All right, so torque analysis, similar to our force analysis. We identify that object. We then make sure that we identify all the interactions acting on the object. We draw our free body diagram, paying attention to where we place that pivot point so that we can make our lives easier. In this case, getting rid of 2 torques that we wouldn't be able to calculate. We then look at the torque acting on each one. I strongly encourage you to keep even the 2 that are 0 in your analysis so that you're making sure you're doing it properly as well as fully justifying your work. Recognizing our directions of the torque. For those of you who are taking a calculus-based or algebra-based class, you will probably be doing more angular work, and so that sign or of 90 or sign of negative 90 would give you those positives and negatives, and then summing our torques and recognizing what it means at the end. Okay, good job.